Okay, fine. Thank you. Good afternoon, each and everyone. We want to thank God once again for keeping us alive up to this particular point. You can't just take it for granted because very many have failed to reach today. And of course, we should not be proud that He has left us, because when we become proud, we may think that we are the best. That's why we have survived. But He has a reason. That's why He has left us. My prayer is that He sent the Spirit to open our eyes to see the purpose why He has kept us alive up to this point. We are starting our lesson right away with an opening prayer, and I'll request Benedict to unmute and he prays for us. Benedict, can you unmute and you pray for us?
Lord Almighty Father, we first thank you for the gift of this new day given to us. We thank you for the gift of our lives. We thank you for the gift of each and everything that you have done to us. Mighty Father, I dedicate to you this lesson. Come and bless the teacher who is going to teach us. Be with us, students. May open our minds so that we can receive each and everything our teacher will be teaching to us. I manage to pray through Jesus Christ our Lord. Amen.
Thank you so much for that wonderful prayer. I believe God has heard our prayer and is going to answer our prayer accordingly. This program is made possible by Edify Uganda. This is the organization which is sponsoring each and every program, which you see cutting across from nursery up to secondary. Edify is working hand in hand with the Christian School Owners Association under the brain of ICT Teachers Association of Uganda. They're the technical people behind all this program. So we thank God for Edify. We thank God for Christian School Owners Association and also for ITAO. We pray that God continue to do good to them so that they can bless the whole world. Today, we are in Senior 5 Physics, of course. I don't expect anybody in Senior 1 or 2 to be here. If you're here, then you're in the wrong place for now. I beg that you leave the class and you go and join another one. Senior Physics are my name. For those who have just joined today, I'm called Teacher Daniel ALIRA. And down there is my contact and my email as well. In case of anything, you can contact me and then we talk into length. So my name is Daniel. We are handling Physics Paper 1, and specifically we are on heat and thermodynamics. We had enough discussion. We did a lot of discussions. And today we are going to see specific heat capacity of a solid. But before we see specific heat capacity of a solid, can I see by show of hands those who attended the last lesson, and you tell us briefly what we studied in the last lesson? Can I see by show of hands those who attended the last lesson, and you tell us briefly what we studied in the last lesson? Hello, you can raise up your hand. I see Buami Benjamin, I see Bob Muller, I see Blackman, I see John Ellipse. I see very many people. I see Raymond, I see Saloa, Nabudu, I see Shana, I see Steven, I have a Mark. Please, among you, is there anyone who attended the last lesson? And if yes, can you tell us briefly what we studied? Hello? Please, let's respond. Let's respond, please, for sure. Let's respond. Do you want to tell me that all of you never attended the last lesson? Yes, I see Bob Mola with the hands up. Bob? Unmute.
Good afternoon, teacher.
Good afternoon. How are you, Bob?
I'm fine.
Oh, good.
And in the last lesson, we looked at pyrometers, and we said that there were basically two
Yes.
radiation pyrometers, which respond to light and heat,
Uh-huh.
and then optical pyrometers, which only respond to light.
Very good, very good, very good. Good, 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 good. I guess we also saw why a pyrometer is quite different from other thermometers, right?
Yes.
Yeah, what did you say about that? Why is that other pyrometers are different from other thermometers?
Pyrometers do not require actual contact with the
Very
body
good.
in which the temperature is being measured.
Very good, Bob. Bob, you're very serious. You're following the lesson very well. That is great. They do not require body contact. For you to measure the temperature, no, you don't need to bring the body in contact with what? With a pyrometer. In other words, it's like a remote something like that. It's a remote thermometer. Do you get that? And while other thermometers, you need to bring them in contact with the body. That was good. Did you check in the Google Classroom? I told you I was going to post some work for thermometry. All questions which have ever been asked by your neighbor, I've already posted them on our Google Classroom. Did you check there, Bob? Bob, did you check there? You can unmute.
Actually, at the last lesson, I wasn't here live, but I went to YouTube and got it from there.
Yeah, you saw it in YouTube, okay?
Yeah.
You attended, you watched the lesson from YouTube.
Yes.
Oh, that's great. That's great. That's great. So Benjamin is saying that yes, we saw them. Fine. Please make the basis of them. Good, good, good. Thank you so much. So we saw pyrometers, optical pyrometers. We saw even Bob says even on WhatsApp group. Yeah, I posted both on our page, that is WhatsApp page, and also I posted on the on our Google Classroom. Please make the best use of them. There are some resourceful questions there, which will help you to revise very well thermometry. Today we are going to see specific heat capacity of a solid. Specific heat capacity of a solid. Let me ask, who is a good Christian here? Is there any good Christian here? You can say yes on the what? You raise up your hand if you're a good Christian. If you're a good Christian, you raise up the hand. Benjamin, let me hope you're not lying. We shall get to know whether you're lying or not. Benjamin says he's a good Christian. Benjamin?
Yes, sir. Good afternoon, sir.
Good afternoon. Are you a good Christian? Are you a good Christian?
Of course, a real Catholic. Yeah.
Now, Benjamin.
Yes, sir.
The whole world is seeing you right now, okay?
Mm-hmm.
We shall prove whether you're a good Christian, okay?
Yeah.
You hear very well, okay? You hear very well.
Yeah.
Without seeing on my screen, okay?
Uh-huh.
Define the term heat capacity.
Heat
The
capacity.
rest you listen very well, and you help me to judge Benjamin. Benjamin?
Yes, sir.
Without seeing on my screen, define the term heat capacity.
What if I have the same definition? Won't you say that?
Benjamin, okay, you give us the same definition which you have.
Okay. Heat capacity.
Yes.
Is the amount of heat.
Yes.
Had to raise
the
pressure of any mass of a substance through 1 Kelvin.
Through 1 Kelvin.
Yeah.
I'm not going to comment, but people have had your definition and they have seen whether you have seen on my board or not. And they Kale, thank you so much, Benjamin. Okay.
I've not used by 1 Kelvin, so I'm a good.
I see you have not used by. So specific capacity, I mean heat capacity is always denoted by capital C. That is heat capacity. So heat capacity is the quantity of heat which is required to raise the temperature of any given mass of a substance by 1 watt, by 1 Kelvin. So that's heat capacity. So it's denoted by capital C. And in physics, heat energy is denoted by Q. This is Q. This Q stands for heat. You see capital C. Some people, they use small h, I mean capital H. Capital C, capital H in physics, that is heat capacity. Heat capacity is the quantity of heat which is required to raise the temperature of any given mass of a substance by 1 Kelvin. I can easily say, and I can confidently say, heat capacity is the heat per unit temperature. Heat per unit what? Temperature. In other words, if I talk of heat capacity, capital C is the same as Q, which is heat, divided by the unit temperature, which is delta theta. Change in temperature is delta. This is delta theta. So that means that heat Q, when I cross multiply, you realize that heat Q is the same as C times delta what? Delta theta. So this is heat. Heat is given by the product of heat capacity times the change in temperature. That is heat capacity. So heat capacity is the quantity of heat which is required to raise the temperature of any given mass of a substance by 1 Kelvin. Who can give us the SI unit of heat capacity? You can raise up your hand and give us the SI unit of heat capacity, or you can put for me in you can put for me in the chat. Raise up the hand, or you put for me in the chat. SI unit of heat capacity. Yes, Bob Mola. Bob Mola. Bob Mola. First unmute, yeah.
The SI unit it's joules per Kelvin.
Joules per Kelvin. Very good, Bob. Very, very good. It is in joules per Kelvin. So you're saying heat capacity is the quantity of heat which is required to raise the temperature of 1 kilogram mass of a substance. Heat capacity, quantity of heat required to raise the temperature of any given mass of a substance by 1 Kelvin. So you're saying that heat capacity, capital C, is given by Q. Q, I have told you, is already heat divided by change in what? Change in temperature. So when you make Q the subject of the formula, you get your Q to be equal to C delta theta. And the unit molar has just given it to us as joules per what? Joules per Kelvin. Now, that takes us to what you're calling to be specific heat capacity. What is specific heat capacity? And its SI unit, of course. Raise up the hand and give me specific heat capacity. The definition, I see Nabdudu Saula. Nabdudu Saula?
Yes, please, teacher.
Good afternoon. How are you today?
I'm fine, teacher.
Thank you.
Specific heat capacity is the amount of heat required to raise the temperature of 1 kilogram mass of a substance by 1 Kelvin.
Munonga. Thank you. So
is joule per kilogram per Kelvin.
Do you know what? You go and look for the admission letter of a university, you go and study for sure engineering. Oh my God. The SI unit is even joules per kilogram per Kelvin. I'm so happy to have Joy Lovins here. Joy Lovins, how are you?
I'm good, sir.
Oh, I'm very happy you're here, though you joined when we had already started, okay?
Yes.
Can you give us the version of your specific heat capacity?
I have the same definition.
Okay, please. I'm happy to have Benjamin here. Benjamin, good afternoon.
Good afternoon, sir.
How are you today, my brother?
I'm fine. Last week I missed the lesson.
Oh, we miss you in class, seriously. The moment you're not in my class, man, just know that I don't feel okay. What was the problem? Have you solved the problem?
Yeah, it was about the timetable.
Oh, you would have inboxed me. I would send for you timetable right away.
But I got it on YouTube.
Okay, please, fine, thank you. So specific heat capacity is the quantity of heat which is required to raise the temperature of 1 kilogram mass of a substance by 1 Kelvin. 1 kilogram mass. The other one was just any mass, but here it is specifically 1 kilogram mass. So that means specific capacity. We denote it with a small c. It is heat, which is our Q, divided by, first of all, mass. We need a unit mass. Then secondly, we need a unit change in temperature. That is delta theta. So it is mass times delta theta, Q over mass times delta theta. That is specific heat capacity. Now, if I want to make heat the subject of the formula, you can see that our heat is the same as specific heat capacity times the mass times delta theta. Oh my God. This is heat. Heat in terms of specific heat capacity is given by this. What about heat in terms of heat capacity? Heat in terms of heat capacity, we saw it. It was just capital C delta what? Delta theta. This was heat in terms of heat capacity, and this is heat in terms of specific heat capacity. Now, when you look at this, you realize that the left-hand side are the same. So we expect the right-hand side also to be the same. So that means that if I cross out this, I'll also cross out that. So I remain with the specific heat capacity, capital C, heat capacity, capital C, to be equals to small c times the mass. Are we able to see that? Hello, let me know. Are we able to see that heat capacity is specific heat capacity times the mass from these two equations? Please let me know in the chat, or you can give me a signal. Joe Lavin says yes. Are we able to see that heat capacity is specific heat capacity times that? Wesonga says yes. Wesonga, how are you, Wesonga, for sure? You people, I'm praying to God that one day we conduct our lessons live so that at least we interact, we see how lessons can move very well. Wesonga, can you unmute? Hello, Wesonga. Wesonga. Okay. She's going to unmute. I mean, he's going to unmute after. So yes, sir. Fortunately says yes, sir. Bob Moore says yes, sir. Good. So the relationship between specific heat capacity and heat capacity is here. Heat capacity is the product of specific heat capacity times the mass of the object. That is heat capacity. So this expression is very important because in calculations, we shall always be given like a heat capacity. They can decide to give you heat capacity. When they give you heat capacity, don't expect specific heat capacity and the mass, because heat capacity alone is already the mass and specific heat capacity. That was good. So that is that when it comes to specific heat capacity. Now we are saying specific capacity is the quantity of heat which is required to raise the temperature of 1 kilogram mass of a substance by 1 Kelvin. When you look at this expression, This is an expression for specific heat capacity, small c. Please, capital C was heat capacity, small c specific heat capacity, which is given by 2 over m delta theta. Making you the subject of the formula, you get 2 to be mc delta theta. I like this expression right away from O level. I used to like this expression for sure, but I don't like delta theta. One day our teacher introduced delta theta, I got lost. Me, I was used to this. MC into theta 2 minus theta what? Theta 1. This is the expression I used to like. But whenever the teacher would introduce delta theta, say now delta from where? But delta theta is just change in temperature. So if the initial temperature was theta 1 and the final temperature became theta 2, that means that the change in temperature is the final temperature minus the initial temperature. The unit, just like how we were given, is joules per kilogram per Kelvin. Oh my God. Let's see relationship between capital C and small c. In other words, relationship between heat capacity and specific heat capacity. We get it from where? From the other two equations, we wrote heat in terms of heat capacity. Then we wrote it in terms of specific heat capacity. But both of them being heat, that means this side is also supposed to be the same as this side. That's why you have C delta theta, which is this side for this, must be the same as MC delta theta. So delta theta will go. We remain with the C capital should be equals to MC, as simple as that, as simple as eating porridge. Oh, Raymond. Hello, Raymond. Raymond. Hello, Raymond. Raymond. Okay, Steve. Steven. Hello, Steve. Steve. Okay. Raymond, yes. Raymond. Yes, Raymond. Your network, Raymond. Raymond. Oh, sorry. It's okay. Fortunate. Hello, Fortunate.
Yes, sir.
How are you? How are you?
I'm fine, sir, and listening.
Oh, good. Is everything okay so far?
So everything is okay.
Oh, that's great. Please, if anything is not going on well, don't hesitate. Raise up the hand. Go in the chat. Say, "Gwe Musaja Sebo, sir." Can you repeat this? Okay.
Yes, sir.
Good. Joy Lavin says, "We continue, sir. Everything is fine." Good, 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 good. So let's look at a calculation on this. How do we deal with this? Calculate the quantity of heat, that is 2. They're saying calculate the quantity of heat, that is 2, which is required to raise the temperature of a metal block with heat capacity. This is heat capacity, capital C, with heat capacity of 23.1 joules per Kelvin by 30 degrees. Calculate the quantity of heat which is required to raise the temperature of a metal block with heat capacity 23.1 joules per Kelvin by 30 degrees. So when they say by, that means that's already change in what? That means it's already change in temperature. So if it's already change in temperature, we call it to be delta what? Delta theta is the same as 30 degrees Celsius. So if they want the quantity of heat, we have already seen quantity of heat in terms of heat capacity. It is just heat capacity times change in what? Change in temperature. So this will be just heat capacity, which is 23.1, then times 30. Those one with the calculator, can you get for us the answer? What do you get? I see Joy Lovins with the hands up. She has taken it down. Those one with the calculator, what do you get when you multiply? Yes, Joy Lovins.
693.
693. Thank you so much. 693.
Joules per Kelvin.
It is heat. Heat is in joules, Joy Lovins, okay?
Yes. Sorry.
Okay, good. So it is 693 joules. Fortunate says 693. Benjamin says 693. Kemigisha, Edna. But Kemigisha, have you ever talked in my class for sure? Raise up your hand, Kemigisha. Kemigisha, can you raise up the hand? I've seen you. Kemigisha, can you unmute? Kemigisha?
Yes, teacher.
Good afternoon.
Good afternoon, teacher.
Have you ever talked in my class for sure, Kemigisha?
No.
It is
My
a crime not
first
to. It is a crime not to talk in my class for sure, my sister.
It's my first time.
It's your first time. Oh. So can you say hi to the whole world?
Hi, people.
Okay, please. Fine. Thank you so much. Make sure you contribute, okay?
Yes, teacher.
Fine. Yoshi says, Yasin Karim says 692, 693 joules. So this will be the quantity of heat which would be required to raise the temperature of any given mass of copper, of metal block by this. Now, I have a simple question. We are talking about heat capacity, heat capacity, heat capacity, heat capacity. If somebody asks you that heat capacity of water, specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Listen to my statement very well. Specific capacity of water is 4,200 joules per kilogram per Kelvin. What does the statement mean? Please, can you give me the answer to that? Because we need to understand what is this specific capacity. Some of us, we just define this is a quantity of heat required to raise the temperature of 1 kilogram mass of a substance by 1 Kelvin. Now, if I tell you that water has specific capacity of 4,200 joules per kilogram per Kelvin, what does it mean? Yes, Saloa.
Teacher, for me, I think it means that 4,200 joules of energy are required to raise the mass of the substance by 1 Kelvin.
Of a substance by 1 Kelvin. Good, thank you. Let me see in the chat. Teacher, aren't we like supposed to convert the temperature to Kelvin? That is Wesonga. Oh, Wesonga. We don't need to convert to Kelvin. We don't need to convert this to Kelvin. 1 Kelvin is almost like 1 watt. This is temperature change. This is delta theta. This is temperature change, delta theta. So if let's say we had 27 degrees Celsius, then it changed to 30 degrees Celsius. So the change in temperature here is just a 10. Isn't it 10 members? What is 37 minus 27, which is 10. But what is this one in Kelvin? 27 in Kelvin, that is 300. Because you add to 273. So this is 300 Kelvin. Then if I convert this, this is 300 and what? What is this? What is 37 degrees Celsius in Kelvin? Can somebody give me the answer? You add 300, 270. What do you get? 273 plus 37. Don't you get to 310? Yes. You get 300 and what? 310. We are trying to see whether it will make any difference, converting the temperature and not converting. So when I get the difference, what is the difference here? Is it 10? It is still 10. You can see that it's still 10. I don't know whether you get me there. When you get the difference, it's still 10. So it was 10 when it was in degrees Celsius. The change in temperature was 10. And when we converted to Kelvin, the change in temperature was still what? 10. So there's no effect of not changing. And that's why we don't need to change. Okay? Let me hope I've answered you. Who was that? Wesonga. Wesonga, can you raise up the hand? Wesonga. We have seen you. Wesonga? Hello, Wesonga?
Yes, teacher.
Have I answered your question?
No, teacher. Okay, what was confusing me is that when it affects the unit in which we write the final answer in, because the final answer is being joules per Kelvin, but then if the change in temperature is in Celsius, it doesn't make sense for me.
Okay, the issue is per Kelvin, okay? Per Kelvin, do you see this?
Yes.
It is like per degree Celsius. Is that fine? Because we have seen already 1 Kelvin is changing by 1 Kelvin is like changing 1 degree Celsius. Do you get that?
Yes.
So, change by 1 Kelvin per unit temperature rise. When you say per unit temperature rise, that means that the temperature has changed by only either 1 Kelvin or 1. When it changes by 1 Kelvin, it's the same as change by 1 degrees Celsius. However, we take the standard unit, and that is the thermodynamic temperature, which is Kelvin. Okay?
Okay.
Oh, fine. Thank you. Good. So we are done with this calculation. Let's go to this is a solution. We have already seen this, and we have already got this value as 693 joules. Let's see an experiment to determine the specific heat capacity of a solid using electrical method. I like electrical method more than any other method. I don't know the reason, but I think it's just very direct. Yeah, it is very direct, and you can do it a little bit faster. Now, can I pick somebody from there to describe for us an experiment to determine the specific heat capacity of a solid using electrical method? Who can describe for us that? Yes, Benjamin.
No.
According to the diagram.
Yes. Wesonga, can you mute? Okay, Benjamin, you can go on.
According to the diagram.
Yes.
2 holes are drilled into the metal.
Yes.
Whose specific capacity is required.
Yes.
Then the mass of the metal M is measured and its initial temperature theta determined.
Very good.
Then the metal is carefully lagged to minimize heat losses.
Very good.
A thermometer is inserted in one of the holes and a heater connected to source of electrical energy is also inserted in the hole.
Very good.
Then the heater is switched on for a time during which temperature of the metal rises to temperature theta 2.
Okay.
Then the potential difference V and the current I during the time T are determined from the voltmeter and ammeter, respectively.
Very good.
Assuming there is no heat losses or there is negligible heat loss, electrical energy supplied through the heater is equal to heater gained by the metal.
Oh my God, great.
Yeah,
Then from there, you write the equation, right?
Yeah, we write our equation.
Oh, thank you so much, Benjamin, for sure. Thank you so much. Thank you, Munonga. There's somebody who has asked a question here. Fortunate says, sir, are you forgetting the question of specific capacity of water? Hey, somebody gave us the answer. Because the question was, when I talk about specific capacity of water is 4,200 joules per kilogram per Kelvin, it means that the amount of heat which is required to raise the temperature of 1 kilogram mass of water by 1 Kelvin is 4,200 joules. Or you can say 4,200 joules of heat is required to raise the temperature of 1 kilogram mass of water by 1 Kelvin. Let me hope I've answered that question, Fortunate. Oh, thanks, sir. That's Fortunate. It's okay, please. Fine. We are here for one another. So we are talking about specific heat capacity of a solid. How do we determine the specific heat capacity of a solid? To determine the specific capacity of a solid, of course, there are very many methods. We are talking about electrical method. So what you do, you make, just like how Benjamin has done it for us. Actually, Benjamin, you have already taught my lesson. So you get your solid, you make it in form of a block. After making it in form of a block, you make these two holes. You make these two holes. There's hole 1, then there's hole what? There's hole 2. After making these two holes, you first weigh the mass of this solid. You can call the mass to be m. After weighing the mass, you use this thermometer, you insert it in one of the holes. Then you read and record the initial temperature. You can call it to be theta 1. After that, in the other hole, you insert the heater, of which this heater is connected to the power source, as you can see. Now, you put on the switch. You turn the switch on, and you adjust this rheostat so that a certain value of current I flows through the heater. So you adjust the rheostat so that the current flowing through the heater is I. And the PD across the heater is V. So you allow this current to flow through the heater until when the thermometer records another change in temperature, records another temperature, until when the temperature of the body of the block increases to a certain value, theta 2. When the temperature increases to a certain value of theta 2, you determine the time through which the current was flowing through the heater. You determine the time taken for the current to flow. Then you call that time taken to be what? To be T. If the current has flown for 30 seconds, then you determine that time using a stop clock. Then from there, you make one assumption. And that assumption is not very correct. And the assumption is, assuming there is no heat loss to the surrounding. There's nowhere there can be no heat loss to the surrounding. Yes, much as we have the lagging, this lagging is to just minimize, but it cannot prevent. Then two, even we don't take into the account the heat gained by the thermometer, because the thermometer will eventually be hot and it will have some heat already, but we don't take into account the heat gained by the thermometer. Even the heater itself has its own heat. So we make that assumption, but that assumption has some limitations. The first one is the source of the error. The source of the error here is the heat taken or the heat gained by the thermometer and the heater is not taken into consideration. Even the heat gained by the jacket here, by the lugging, is also not taken into consideration. And so what you're saying that assuming there is no heat loss to the surrounding is not a very nice assumption. But if we assume and we close our eyes and we say that if there's no heat loss to the surrounding, then the total heat supplied by the heater will be the heat gained by this block. So heat supplied by the heater, remember the heater is connected to the electricity. So the heat supplied by the heater is the electrical what? Electrical energy. So what's the expression for electrical energy? Those who have already studied current electricity, can you raise up the hand and you tell us expression for electrical energy? You can even write for me in the chat. Expression for electrical energy. But this, who is black man? Hello, Eric. Eric? Eric? Hello, Eric? Hello, Eric? Hello, Eric? How are you, Eric? Oh, Eric? Okay, Crispus Kumini. Crispus? Hello, Crispus.
Yes, sir.
How are you? How are you, Crispus?
I'm fine, sir.
Is everything okay?
Yes, sir. I've just joined and
Oh, sorry.
Yes, sir.
So our lesson start at exactly midday, okay?
Okay.
Make sure you get there at exactly midday. We speak only physics here. We don't speak any other thing here, okay?
Okay, sir.
Okay, please. Fine, thank you. Somebody has already given me. Yes, John Ellipse. John.
Master, more clarification about that experiment.
Sorry?
More clarification about that experiment.
Oh, please, let me do that in a very short time. Good. We are saying you get the block. I mean, you get the body, the solid, whose temperature is required. I mean, whose specific capacity is required. You get the solid. You get the solid, whose specific heat capacity is required. Then you make it in form of a block. You see, this is like a block. After making it in form of a block, you drill two holes. The first hole is here, and you drill the second hole here. After drilling, what you do, you measure the mass of that thing, of that block. You call it to be M. Then you insert the thermometer into the first hole. Then after that, you determine its initial temperature, θ1. You insert the heater in the other hole, connect the switch K on, and then allow the current to flow for a certain time T until when the temperature increases to θ2. You read V and I after that. Then you're saying if there's no heat loss to the surrounding, then electrical energy, I've already seen people have already given me the answer in the chat. The electrical energy is VIT. Good. Yassin, Karim, and Nabudu, Shalwa, you have given me the answers already. So the electrical energy is VIT. The electrical energy supplied, VIT, should be equal to heat gain by the solid. And we said heat gain by the solid is the mass of the solid, specific heat capacity of the solid, then the change in temperature will be θ2 minus θ1. Then from there, remember, we want C. So we want C, we make it the subject of the formula. That means that mass, C, will be the same as VIT VIT divided by M into theta 2 minus theta 1. Is that clear, members, where specific capacity can be calculated? Please, can you let me know? Here you determine the specific capacity already. Is that clear, members? Hello, you can let me know. If it's not clear, you can see raise up the hand. I pick you. I see where the problem is, so that, yes, teacher is clear. That is from Benjamin. Yes, Joy Lavin says somehow. Joy Lavin, what is not very clear, so that I make it clear. Okay. Fortunate says, yeah, it's somehow okay. Good. Okay. It's okay. That is Marilyn. Fine, thank you. So, yes, sir. Eric Blackman says it's okay. Good, 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 good. Very clear. That is Andre. Very clear. People are saying, okay, fine. So that is how we can determine specific heat capacity of a solid. Sometimes we are given the power of this heater. Remember, electrical power is the same as VI. So if the electrical power is VI, that means I can even come here, I remove the whole of this one, the whole of VI, then I replace with it P. So that means that C is going to be equals to PT. It is P times time divided by M into theta 2 minus theta 1. Hope this is clear. So if V and I are not known, then I need the power. Power is VI. So I remove VI, I replace with what? I replace with the power. Then from there, I get PT over M into theta 2 minus theta 1. Is that clear? Hello? Is that clear? Yeah, Nabudu says, yeah, it's clear. Yes, yes, Bob Muller. Yes, everyone is saying it's clear, clear. Yes, yes, Benjamin Yasim says, yes, good. So that is how you can determine the specific heat capacity of a solid using electrical method. Let me take you through the processes very fast. You're saying a solid of block of mass, a solid block of a metal is drilled with 2 holes, one for the thermometer and the other one for electrical heat, and filled with the mercury for good thermal conduction. Now, I want to make this point very clear. The 2 holes which you drill in the 2 holes which you drill in the solid, you have to put there some oil, or you put there mercury. Why putting mercury or oil? Is to enable heat conduction very fast. It's just for good thermal conduction. Between the block and the thermometer, remember you're going to insert the thermometer in the hole. So the thermometer should go and find there what? Some liquid, like a good conductor, a liquid which is a good conductor. So in this case, we take mercury. So mercury is there just to make sure that there is good thermal contact between mercury, between the block and the thermometer. Hope that is very clear. So you have to put it there so that there is good thermal conduction. Then after that, we are saying that the mass M of the block is determined and the initial temperature theta 1 recorded. You switch the heater on and the stop clock at the same time, and you allow the current to flow, current I and voltmeter V, for a certain time T until when the temperature increases. So when the temperature has risen appreciably, the current is stopped and the time t of heating is noted. And that very final temperature, theta 2, is read and recorded. Then you make that one assumption that if there is no heat loss to the surrounding, if there is no heat loss to the surrounding, if you have no heat loss to the surrounding, then the total heat supplied by the heater should be the same as heat gain by the block. Then you write your equation. Total heat supplied by the heater is VIT, which I've already talked about, equals to MC into theta 2 minus theta 1. So C is calculated from VIT over M into theta 2 minus theta 1. Benjamin says, what if I say, assuming negligible heat loss? Yes, that is very correct, Benjamin. Assuming negligible heat loss, that is okay. That means you are neglecting the heat loss to the surrounding. So from there, we go to the note. So note that electrical power is VI, and thus it means that our C, where there was VI in the first equation, we replace it with P. So you get PT over M into theta 2 minus theta 1. Some of these things I'd already discussed with you. Let's look at calculation number 1. If there's no question. If there's question, please ask. There's no question, let's look at calculation number 1. So we have a steady current of 12 ampere. That is I. I is 12 ampere. So let me call this to be I. I is 12 ampere. And a PD of 240 volts. So this is my V 240 volts. Is passed through a block of mass 1,500 grams. We convert this one to kilogram by dividing by 1,000. So mass is 1.5 kilogram. For 1.5 minutes, 1.5 minutes, that is the time, we convert it to seconds. This will be 90 seconds. If the temperature of the block rises from, so this becomes our theta 1. It rises from, this becomes theta 1. 2, so this becomes theta what? Theta 2. If the temperature of the block rises from 25 degrees Celsius to 80 degrees Celsius, calculate the specific heat capacity. For sure, this is not physics. I don't know what it is, but it is as simple as eating porridge for sure. Calculate the specific heat capacity. So we say, since this is the heater, it is an electrical current, it's an electrical energy. So you say VIT should be equals to MC into theta 2 minus theta 1, if there's no heat loss to the surrounding. So V is already 240. I is already 12. T is already 90. Oh my God. Should be equals to M, which is 1.5, into, times C into theta 2, which is 80, minus theta 1, which is 25. Good. When you multiply this by this by this, what do you get? Please give me the answer. What do you get? Who is having a calculator? If you have a calculator, raise up the hand. I unmute you. If you have a calculator, raise up your hand. I unmute you. Hello? Those are the calculators. Yes, I see Benjamin and Fortunate, they both have. Yes, yes, Fortunate, can you unmute?
Yes, sir.
What is 2,240 times 12 times 90?
You get 259, then 200.
259.
1,200.
200. Okay.
Yeah.
Good. Should be equal to. So here we shall have 80 minus 25. What do you get?
55.
Times 1.5. What do you get?
82.5.
82.5. C. Then to get C, you divide all through by 82.5, no, sir?
Yes.
So what is C?
That is 3,000.
3,000.
141.
141.
0.818.
0.8182.
Yeah.
Good. This is in joules per kilogram per watt per Kelvin. Is that okay, members? Okay, good. People are giving me the answers. Benjamin says 3,141.82. Joe Levin says 3,141. Joe Levin, you have to write to some decimal places. Good, 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 good. Let's wind up. Let's wind up. Then heat capacity. Heat capacity is they want the heat capacity of 4 kilogram mass. So heat capacity, we had already seen that heat capacity, it is the mass times specific heat capacity. So if we already know the specific capacity as this, we just multiply by this mass. What do you get when you multiply?
I get 12,000.
12,000.
567.
567.3. 0.3. Good, thank you. This is in joules per Kelvin. Thank you so much. So that is how you can go about with such a calculation. Good, 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 good. Is there any question? Please let me know in the chat. Is there any question? Is there any question? Is everything clear? Yes, Benjamin has the hand up. Yes, Benjamin.
So I just have a question about last week's lesson.
Yes, yes.
About the mode of operation of an optical pyrometer.
Yes.
When they ask us the mode of operation, I'm supposed also to draw an illustration or that diagram.
You draw that diagram, okay?
Okay.
Yeah, you draw that diagram. Okay, good. Is there any other question? Because I see people are saying, yes, teacher, it is very clear. It's very clear, it's very clear. Okay, fine. So now, our time has gone. We have already seen this. Given I, we already had I 12, V, time, and that. So we just converted. Theta 1 was 25, theta 2 was this. So I use this VIT equals to that. So we get that 3141.8182 joules per kilogram per Kelvin. Then for part 2, they wanted the heat capacity for 4 kilogram mass. So heat capacity for 4 kilogram mass, Benjamin says, thank teacher for the lesson. Heat capacity for 4 kilogram mass, you multiply heat capacity by specific, you multiply specific capacity by that mass. So that's why you will see this. the heat capacity of 4 kilogram mass of the block. Heat capacity, capital C, is small c times mass. So we multiply this by that, you get as joules per Kelvin. So here is your assignment. I'm going to put it on Google Classroom. You'll do it, then you will submit it also for marking from there. For those of you who have not yet joined Google Classroom, the Google Classroom code is there. Google Classroom code is there. For those who have not yet joined. And this lesson has been made possible with the funding from Edify Uganda. We say thank God for them, with the Christian School Owners Association and ITAO Uganda. I thank you so much for being part of this. May God protect you, keep you safe during this hard time. I beg to stop here. We can have a nice day. Oh, Fortunate says that I read. Fortunate, remain in class. I read for you the code. Let me read for you the code. Fortunate, the code is small I. Fortunate, the code is small I. 5, small I, 5, 6, small s, small I, small f, and a 5. Let me even put it on the chart. Let me put it in the chart. The Google Classroom code is there. Small I, 5, 6, small s, small I, small f, then a 5. Let me hope you are clear now. Fortunate, Fortunate, are you okay now? Hello, Fortunate. We are ending the lesson. So you join there, and our assignment, I'm going to post it right away after this lesson. Thank you so much for being part of this. See you in the next lesson. Goodbye for now.